As a continuation to our lecture on melee and more, in this lecture, we'll be designing a finite state machine, and which will be able to recognize a particular pattern. So for our explanation, we are using the problem that you have done in the theory. So I'll not go into the details of how this state diagram came into action and anything else. What I'll do is I'll read out the problem statement and I'll be building a code based on this state diagram. So the problem statement says derive the state diagram of of a finite state machine that has input of W and output of Z. Remember, clock and reset are given. You don't have to. Those are not generally mentioned in question. Those are assume that you'll understand those are there. The machine has to generate Z is equal to 1 when four consecutive values of W are 1001 or 1111. Otherwise, Z is equal to 0. Overlapping input patterns are allowed and an example of the desired behavior is given. Okay. Now this is our finite state machine, or sorry, this is a state diagram that we have already drawn. We have already discussed in theory class, and I'm assuming that you have come to visit this lecture after attending the lectures of theory class. So what we need to do is at first we open a project like we always do. We define the directory. In my case, it would be in local drive D. Okay. In the directory, I name it FSM2. Then file name, no need, flex 10K. We have to check all these are Verilog or not. And we press finish. After finishing, we open a new Verilog HDL file. So the process remains the same, the process that we followed in melee or more. The first thing is we define the inputs and outputs. So module FSM2 W clock reset Z. Then we define input as W clock reset, output as Z output. Now, one thing is to be noted. You observe it very carefully. Is it a melee or mode? See, it's written four consecutive values, not four preceding values. And again, if you see the example 1, 1, 1, 1, as long as we get the fourth one in the input, we get 1 in output. That is, it doesn't, the output is not changed in the next cycle. That is, output is dependent on present input. So this is a melee. Since it's melee, the output does not have to be considered a register. We can just consider it as a normal output. And we have to define present state. Now, present state, what is the total number of states? 0, 1, 2, 3, 4, 5, 6, 7. There are a total of 8 states. So in order to define 8 in binary, in order to write 8 different numbers in binary, we need 3 bits from 000 to 111. 000 corresponding to 0, 0, and 111 corresponding to 87. So we need 3 bits. So we put colon 220 PS. This part over here is really important because you understand it actually indicates the number of states that are there. Again, we have to select parameter. Again, 2 colon 0. S0 is equal to 0. S1 is equal to 1. S2 is equal to 2. S3 is equal to 3. S4 is equal to 4. S6 and S7. So we have defined our parameters. Now if you remember it correctly, what we do, we define the output. Z is equal to, in this state diagram, we see that output is equal to 1 in state S7 and state S4. So we can define it like that, like this. Z is equal to, present state is equal to S4, or present state is equal to S7. It indicates this indicates that if any of these conditions, present state is S4 or present state is S7, if any of the condition is true, then Z will become 1. So this is all right. Then we always add red pause edge fuck if reset is 1, we turn present state is equal, we write present state is equal to S0, else begin end. So else, within the else, what we would use case, and the case variable is present state. If present state is S0, then what happens? If W equal to 1, we move to S1. Present state is equal to S1. Else present state is equal to S0. So this is for S0. We copy it and we just modify it for S1. For S1, we see W is equal to 0 goes to S2, W is equal to 1 goes to S5. So W is equal to 1 will go to S5, W is equal to 0 will go to S2. Similarly, we can do the same for S3. For S3, W is equal to 1 will go to S4. So, sorry, we at first S2. For S2, W is equal to 0 will go to S3, W is equal to 1 will go to S1. So W is equal to 1 goes to S1, W is equal to 0 goes to S3. Similarly, for S3, W is equal to 1 will go to S4. W is equal to 0 will go to S0. Okay. Now we have to do the same for S4. For S4, W is equal to 1 will go to S5 and W is equal to 0 will go to S2. So here we have S5, here we have S2. For S5, for S5, W is equal to 1 will go to S6, W is equal to 0 will go to S2. So here we have S6, here we have S2. Now for S6, W is equal to 1 will take the present state to S7 and 0 would take it to S2. So here we have S2, here we have S7. And the last state is 7. W is equal to 1 will keep it in S7 and W is equal to 0 will take it to S2. So thus we have defined all the cases. We have to put end case. We have defined all the different states and how they would respond to the present state. And after doing so, we put end module. So we save it. Okay. Now we can see that everything is defined. All the states S0, S1, S2, S3, S4, S5, S6, S7 has been defined. And we have really easily put this with the help of the state diagram. For example, let us take one at a random, S2. From S2, if W is equal to 0, it moves to S3. And if W is equal to 1, it moves to S1. So here we have S2, W is equal to 1, present state will be S1. If 0, present state will be S3. So we can directly write this piece of code from the state diagram. If we know the state diagram well, there is no problem that can stop us. Now let's try to simulate it to check if everything is all right. Okay, not successful. There must have been an error of in line number 6. Oh, in all the cases we have written capital S, but here by mistake we have written small s. Oh no, these are capital S as well. Okay, no. Was there at line 6 it's near equal, it's expecting an identifier. Line 6. Z is equal to, oh sorry, I have forgotten to put assign statement. That's why it's giving me the error. Not successful. There is another error. The error is in line 8. Okay, the line 8 is here. Here equal to double equals 100. Next. Okay, it seems like now the simulation is going all right. We have debugged all the errors. So this place over here is the place where all the error messages are shown. Be very careful. You can debug it really easily if you just take a closer look. Okay, now there is no error. If there is no error, we can go on to our vector waveform file. We do the usual insert node, select all the nodes. We put the readily available clock. The first clock cycle will be our reset. Now let's see the let us see the pattern of W. 0 1 0 4 ones. Okay, here 0, then 1, then 0, then we will have 4 ones. 1 2 3 4 ones. After these 4 ones, we have 2 zeros, 2 ones, 2 zeros, 1. 2 0 2 1, then again 2 0, then 1. Then we have 4 more ones. 1 2 3 4, 4 more ones. Now let us check if it's correct or not. The output would be 0 1 0 1 1 1 1. 0 input is 0 1 0 1 1 1 1. 0 0 1 1 0 0 1 1 1 1 1. 0 0 1 1 0 0 1 1 1 1 1. So the input is correct. We save it. After saving it, as usual, we go into assignments. We change the settings from timing to functional, and we generate functional simulation netlist. Successful. Then we start our simulation. Simulation was successful. Now let us look at the output. The output should be 0 0 0 0 0 0. Sorry, 0 0 0 0 0. 6 zeros and then we get 1. So this positive edge will give us 0. This positive edge gives us 0. Sorry, this positive edge gives us 0. Then this also gives us 0 as output. This gives 0 as output. 3 zeros. Here is our 4th 0 as output. 5th 0 as output. Output is the bottommost graph. 6th 0 as output. On the 7th positive edge, we get 1. So here on the 7th positive edge, we are getting 1 as output. And then what do we get? We get 2 0 1 and 3 zeros 1. Let me clear this up so that it can be seen. Then after this one, we have 2 zeros 1, then 3 zeros 1. Let us check. Now here this positive edge gives us 0 as output. This positive edge also gives us 0 as output. Here we get 1. So 2 zeros, then 1. Then here we have 0, 0, 0, 3 zeros, then 1 again. Then 2 zeros, 2 ones. Let us check. Then this positive edge gives us 0. This edge gives us 0. We have 2 zeros. And then we have this positive edge as 1, this positive edge as 1, 2 ones. So we can see that for the input provided here, we are getting the output. We are getting our expected output. So this output, this pattern recognition is correct, and output Z is being modified with our inputs. So this is how actually our system works, and we are able to design a finite state machine with which we can recognize pattern. Finite state machines can be useful in a lot of different aspects and a lot of different real life problems. For example, finite state machines are being used in traffic control and a lot of other things. So one thing you need to recognize is the key to designing a good finite state machine is to design a good state diagram. If the state diagram is designed, this thing does not take much time. The code is really easy. So be very careful while you design state diagram and practice. And one way to understand whether your state diagram is correct or not is you come to Quartus, you write this short piece of code and you simulate. You put your input and see the output. If the output is correct, your state diagram is correct. If the output is not, there might be some mistake in the state diagram. So Quartus will be a good tool for you to practice your state diagrams as well. That's all for VLSI Lab. Best of luck for your future endeavors. Thank you.